Hello, my name is Matt Westerveld from Metrix CreateSpace, and I am here to present results for DARPA PA 1152, an inexpensive, practical, textile-based computing and communications platform. Our project has four main areas of focus: power storage and charging, durability, cross-garment communications, and modularity at the garment boundary. We do not focus on applications at this time.
This iteration, we spent much of our time structuring graphene with supercapacitors that power our circuits. Because the available research mostly deals with light-scribe DVD-ROM drives, and one of our secondary goals is to provide a manufacturing blueprint for this process, we adjusted the settings of our machine to effectively become a light scribe. Through numerous tests, making small changes to speed, power, and frequency, we fine-tuned the laser to maximize conductivity in our graphene samples. Using the best results from these settings, we have structured our first set of supercapacitors using the new circuit wells. It gives us a reliable and repeatable result using the same equipment that we use to structure our circuit boards. Because of our switch from Pyrolux to Acaflex in our last iteration, we have been able to reliably create single-sided flexible circuits. Lacking double-sided material and the time to order more, we laminated two sheets of single-sided Acaflex together with a fiberglass prepreg in order to create a less flexible but workable medium. This allowed us to move forward with our new board design. We also found that we could run the full production on the laser, eliminating the need for the plotter for production of flex. This simplifies the effort and yields better results. In this new revision, we have cut the assembly time in half. We now have a flexible reference board populated with electronic components.
The goal for this iteration was to develop the actual integration of the physical electronics with the garments with which we're working. In the last iteration, we confirmed that we have very intermittent connectivity between the two garments with the soft contact that we were exploring, which is the shirt draped over pants. So in this iteration, we've had to shift to a different, more stable contact. So what we're looking at in this setup is, again, pants with 6 points of contact and a shirt. But now the shirt tucks into the pants, so our conductive elements are on the outside, they tuck into the shirt, and that we have constant, stable contact. We've also started working with introducing a jacket element and seeing how we can connect the jacket to the pants, potentially through the shirt, and what that connection looks like. In moving forward with the integration of the electronics with the garments, we have pursued two parallel trajectories. One has been to translate our original electronics design into a flexible circuit board, which we have right here. This is a two-sided flexible circuit board that is 20 square centimeters in area. The second part has been to take our base garments and deconstruct them in order to identify the elements with the most potential for actually embedding these flexible circuit boards. So for example, we've taken a shirt sleeve placket, which is kind of standard size, and then figured out how we can get about 20 square centimeters of area on that, which is the equivalent of this piece. And so we could have this be the circuit board, or we could also expand some of the other elements, give us more surface area to work with. So this is a shirt cuff. We could do kind of a more square design or just a much larger board altogether if we wanted to do that. The ultimate goal of this process has been to figure out how we can integrate the electronics in the most unobtrusive way into the garments.
For this iteration of the wireless power transfer hardware, we focused on improving the amplifier in the primary coil. Now, during the last iteration, what we found is that the amplifier had some overheating issues. To fix that, we replaced the MOSFET, and we also looked at tweaking the capacitance values in the capacitor bank. Changing the capacitor values meant that we also had to change the resonant frequency that we were driving the amplifier at, as well as the duty cycle. After making all of these changes, we found that we had very good control over the amplifier. With just 20 volts input, we can get 40 volts peak to peak across the coil. By changing the input power, we changed the output power significantly. And in fact, what we found is that we can get output across the coil of over 500 volts peak to peak. This gives us very fine-grained control of the amount of power that we're transmitting.